All right. So we discussed assumptions last time. Assumption one is linearity in parameters. Assumption two, if you want me to uh, give a recap of any of these assumptions, you have to let me know when I'm going through it. So assumption two is fixed x values or independence between the error term and the x variables. So it says that the x values are assumed to be fixed in repeated samples, and then uh, there is no interdependence between or covariance between x and u. Third assumption says that the mean of the disturbance is zero. Fourth assumption is homoscedasticity, which says that the variance of the errors is constant across all x's. So in other
So
words,
actually, Christy is trying to join in.
okay. So I want to say a little bit about notation here. Mm, I think I have not said much about the notation here. I explained you the concept. So let me talk 2 minutes, 5 minutes about the notation here. So here, as you can see on the screen, that it is written expectation of u minus expectation of u given x whole squared. This expression is the variance of u. So how did we get this? How do you understand this right hand side? How can this be called the variance? So let us start with the definition of variance. What is variance? Variance is nothing but if you find the deviations of any variable, let me call it u. So there's a variable u.
Sir, sorry, but somebody is trying to join in.
Right. So if there's a variable u and you want to find the variance, how would you do that? You take each value of u and subtract the mean of u, square each of these differences, add them all, divide by n. Right? So it's going to be a sort of per unit thing, variance, because it is divided by n.
Excuse me, sir. So Ashwa is trying to enter.
Okay. All right. So, for example, if there's a variable, what is the mean of u? It is sum of u divided by n, right? So you can write the expectation operator to be called as this thing on the right hand side, right? So you can write a u bar or you can write expectation of u. Both are the same things, right? I mean, loosely they are the same. Of course they are different, but loosely you can understand and infer same meaning. So if I ask you, what does this expectation stands for, this part, it stands for adding something and dividing by a number of things. That's it, right? So whatever is there in the parenthesis are written is written here, and then this e stands for this summation sign, and this n at in the denominator, isn't it? So uh, you can borrow this idea to conditional mean also. The only thing is that out of all the u's, you will select some of them which are conditional on something. For example, if you're conditioning u with respect to x, then if x has a ith value, say 5, so you'll take all those x's which have a value of 5 and the corresponding u's will be used in this calculation of mean, right? So you can borrow that, incorporate that idea of conditional mean into the same formula. It doesn't affect anything, just that some a particular subset of all the u's will be taken here for calculating the mean, not all of them, right? So that's the difference between unconditional mean. So if you say expected value of ui, then you have to add all the u's and divide by whatever n is, sum all the u's and divide by number of u's, right? But when you talk about conditional mean or ui given xi, in that case, you will take only some u's which are relevant to this case where x assumes some value. Corresponding u's will be taken. And then again, you will do the same thing. You will add all the u's which are relevant and then divide by number of u's, right? So that's the difference between conditional mean and the mean, the unconditional mean, right? So this is the formula for variance, right? Uh, so if you want to remove this summation and this n from the formula, what you can do is you can simply write expectation operator and write whatever is there inside. So do you agree with this step? I don't want to come and recap it, so please tell me now. I have removed this summation and this n, and then replace these two things by this e, which is the expectation operator from this formula for variance. Sorry, not from here. From here, I have written this as the second step of this formula. And the idea is, I have explained here that what does this E stands for? It stands for summing something and dividing by number of things, right? So can I do that? Do you agree? Is it right?
Yes, sir.
This thing, according to this thing, right? So when you get this, now let me write this same thing here and let me replace u bar with this thing because they are interchangeable, right? So instead of u bar, I am writing expectation of u. And because not all u's are taken here, because we are talking about fixed axis and we are talking about given x for calculating the variance. So I'm going to calculate variance for a given value of x, for example, x2. So I'll take the variance of these u values only, right? So that's the conditional mean. So it doesn't make any difference. because that's why I said in the beginning, this is also conditional variance. This is not variance ui, it is basically variance ui given xi, right? So doesn't matter. I mean, don't worry. You can write it like this also. Let me replace this and then keep everything else same. Now, if you look at the original notation here and what I've written here, they are one and the same. Just look at this box and look at this box, right? So that's the notation part. Uh, One more thing. Uh, this is equal to this, step number 2, because of assumption 3. So let's see what is assumption 3. Assumption 3 says that this is 0, right? So let us put a 0 here. So this thing, this green thing can be 0. Sorry. Okay, I have to just expand it a little. Not this one, I'm sorry. Let me expand it here. Uh, Let me open. If you square this, okay, it will take some space. So did you understand this part? Should I remove what I have written? You can write it somewhere if you want, or I'm removing this part only because this is the basic one which I use just for explanation purposes. It's not a part of the derivation. All right. So I'm continuing from here onwards, right? So left hand side I'm leaving. The right hand side I can open the expectation operator. So for that you have to square the whatever is there inside the brackets first. I'll keep the expectation out and square whatever is there inside. It's going to be a square plus b square minus 2ab. Right? So simple formula. Let me use another color for the parenthesis. And then there is a square here, right? Now, still we want to solve it a little bit. Okay, this becomes ui squared because this is 0 and this is 0. So both the terms become 0 and you're left with this one. And because we are talking about conditional, everything is conditional upon x, right? So you can write it as ui squared given xi because this is also going to be conditional, right? That's how you got the second step here, right? Now you can write it plainly like this expectation of ui squared as it is here. uh, so keep it in mind, I will be using this in future also, that this stands for variance. This stands for variance. So whenever I want to write variance, I'll write expectation of something squared, right? Expectation of something squared will be the variance, right? So you can see the uh, uh, conceptual similarity. If you write expectation of ui, that's the mean. And if you write expectation of ui squared, that's the variance, right? So it's simple to remember, because when you are taking the expectation of something, it's the mean, and when you are taking the expectation of square of something, it's the variance, right? So that's a statistical mathematical fact, that when you take expectation of something, that's the mean, and when you take the expectation of something squared, that's the variance. But there is some catch here. The catch is, I want to clarify that this formula for variance is valid only when mean is zero. Keep that in mind in a solid way, right? So you will see this very often, this expression for variance. You will see variance equals expectation of anything squared, right? But it will not be written why this expression for variance is valid. But you should understand this is only valid when mean is zero, right? In this case, because the mean is zero, because of assumption three here, we can write very plainly that variance can be written like this: variance of ui variance of ui equals expectation of ui squared. You can write it like this. And it doesn't make any difference if you are talking about conditional variance. You can simply add the condition given xi, right? Of course, the mean is not zero. Actually, it is the conditional mean that is zero, right? So that the conditional variance is can be written like this. So a little bit of math here, but I think simple to understand. Now the last point says that, okay, the third step says that this is equal to this if x is non-stochastic, right? So of course we are taking x to be fixed and non-stochastic, and we are taking y to be stochastic and x to be non-stochastic. So you can just leave it away because you have already assumed your x's to be fixed in assumption 2. Carrying on with the same assumption, you need not worry about this part, because we will always be uh, assuming x to be non-stochastic, right? So now what about this? This is just a notation again, uh, which is used for the errors. So if somebody asks you what is the notation used for the variance of ui, you would say it is sigma squared. So we use this terminology that variance of the errors is equal to sigma squared without an I. I have not written sigma I squared, right? Keep it in mind. It's variance ui. There are many u's, so I have a subscript I here, but there are not many sigmas, right? It's one sigma only, and it's a constant. So because of the assumption of homoscedasticity, you should always keep it in mind that you will always write the variance ui to be sigma squared, right? Not sigma I squared, because that would make your errors heteroscedastic, which we don't want, right? So keep that in mind. All right. So if you have any question here, you can ask now at this time. Anything in this math or any concept that you want me to say more about in this whole explanation.
Understood, sir.
Got it, everyone? What about others? If you want, I will explain it more because everything is here in front of my eyes. I've already written everything, so it will not be difficult task for me to explain again if you want anything. Right. So let us move forward. Great. Then assumption of no autocorrelation. Uh, it says that the covariance between different U's is zero, right? So if you are taking U's here, up some U's here, so there is a column called U, lot of U's are there. You separate it on the basis of on some basis, on the basis of X, of course, because it is conditional upon X. So there are some X values, 2, 2, 2, 2, and then 4, 5, 5, 5, 5. So there are two values of X, 2 and 5. If you take all the U's corresponding to 2 and call them UIs, so whatever U's are here in front of 2's will be UIs, and then you write another set of U's where X was 5, and you place all those U's here. And then if you find the covariance between the two set of U's, it should turn out to be 0. And if it is 0, our assumption of no autocorrelation is satisfied. If they turn out to be non-zero, then we will say that we have autocorrelation, right? Uh, Basically, I'll not go into more detail of autocorrelation now, as I said yesterday also, that because we have one full chapter on these violation of assumptions, so I'll discuss it in detail there. Just remember that we are talking about covariance, so that if values of u's do not covary, so the covariance turn out to be 0, we have fulfilled the assumption of no autocorrelation, and that's what we want. So I explained last time also using this graph. This is positive autocorrelation. Of course, you have to. There is some printing mistake here. It is in the book also. Please correct it. We have to have a UI and a UJ according to the notation, right? So it should be J. Right. Then assumptions. Yeah.
So in the assumption 4, can you go back for once? I wanted to ask something. I was going through that.
Yeah.
So can you change this? Yes, sir. So in this, on the right hand side, the calculation, you wrote expectation of ui upon xi whole square to be 0 and 2 ui expectation ui upon x1 to be 0. Sir, why it is 0 here? Can you tell
Okay.
that?
Okay. First thing, to understand is this is not UI upon X, right? This is UI given X.
Given X, yes, sir.
Yeah. So it's not, it's very different from fractions, right? Keep that in mind very clearly. It's not UI upon X, it is UI given X. So it is basically UI conditional upon some X's, a given, right?
Yes, sir.
Second thing is why this is zero. This is zero by assumption three. Assumption three says that this thing is zero. Conditional mean of UI is zero,
Yes, sir. It was
right?
there. Sir,
So keeping that here, conditional mean of UI is zero. I'll put this thing to be zero. Zero squared is zero. Here, conditional mean of xi is zero. Zero times UI times two is also zero. So these two terms vanish, and the only term remaining is this one.
UI
Yeah, UI
square.
squared. UI squared. So I've written conditioned upon x from my side to make you understand that we are talking about conditional use, not unconditional use. So we will always, whenever you write, you take the mean, it has to be the conditional mean only, right?
So this was the explanation of which part, like this
This was the
expectation.
explanation of how do you come from this notation to this notation.
So which your cursor is not moving, sir, right here.
Okay, I am putting it in red box. How do you reach from here to here? You start from this line. So I started from this line and then I solved up to here. That gives us this line and this line.
So your
Right?
system is in a bit lag because I can't see the line where it is going. Like I can only see the box, first box.
Uh,
After that, what you can't see because it goes in a bit lag sometimes.
okay. Let me clear it again. I have removed the lines now. Can you see it removed?
No, sir. It is like on the third line of the assumption on the variance UI, it is just freeze there. Now it has changed.
So there is a red box number one, and there is a red box number two.
So it's because of the explanation that here expectations of u I square, we put it in the equation on the left side. We got the expectation on the left side we solved now on the with the first line on the left you have written expectation UI minus expectations UI uh, given xi whole square.
Yeah, I have
So we
solved this. Yeah.
so when we solve that we here get expectations UI given x1 uh, from there.
Uh, you can directly jump from here to here.
Okay, sir.
I have just squared things.
Yes, sir.
Just open the square, you'll get this thing, and then these two things are zero, and then you'll get this. So it's a two-step process only.
Okay, sir.
Yeah.
Okay. Thank you, sir.
Okay. Then these are two assumptions which we discussed last time. So I think no need to discuss this again. So I'm closing this slide. Now, Now we'll talk about standard errors. What is standard error? So point number one, least square estimates are a function of sample data. So how do you calculate beta 1 hat and beta 2 hat? How do you calculate? You calculate them using x's and y's only, right? So least square estimates, these are the least square estimates. Depend upon these things, x's and y's, right? So these x's and y's are the sample values of x and y. Right? That's nothing but the sample values of x and y, right? So your beta 1 hat and beta 2 hat depends on the sample you have collected and the values that your two variables are taking. If you change the sample, your betas will change. So if you collect another sample on the same two variables from the same population, you will get different values of x, and therefore you will get different beta 1 hat and different beta 2 hat than before. So once you have calculated your beta 1 hat and beta 2 hat, because it will change from sample to sample, you need to have some measure of precision. And that measure of precision is nothing but the standard error. And we write it like this: standard error beta 1 hat, standard error beta 2 hat. So we want to discuss what is this standard error beta 1 hat and beta 2 hat and how it is calculated. Any question? All right.
Understood, sir.
So I'll come to the derivation. I'll show you the how to derive these formulas, but you can note standard error of beta 2 hat can be calculated like this. And standard error beta 1 hat can be calculated like this. Right? So, saying more about the concept of standard error. Standard error is nothing but standard deviation of the sampling distribution of the estimator, and the sampling distribution of an estimator is simply a probability of frequency distribution of the estimator. That means a distribution of the set of values of the estimator obtained from all possible samples of the same size from a given population. Right? Sampling distributions are used to draw inferences about the values of the population parameters on the basis of the values of the estimators calculated from one or more samples. So can anyone summarize the concept of standard error by reading this slide? Okay. Okay, let me put it. First of all, you have one beta 1 hat and one beta 2 hat calculated from a given sample, right? Now you collect, suppose the sample size was 10 and the population size is 1000, suppose, right? So you have collected a sample of 10 from a population of size 1000. And then you used that sample of 10x and 10y values, corresponding x and y, 10 corresponding x and y values to calculate beta 1 hat and beta 2 hat, right? Now, if you collect another sample of 10 from the same population of 1000, you will get another set of x and y values, and then you will have different beta 1 hat and beta 2 hat from the first sample. Do you agree with this?
Yes, sir.
Now, the concept of standard error is that if you collect all possible samples of size 10 from the same population of size 1000. Remember, I'm saying all possible samples of size 10, right? If you do that, and then you calculate beta 1 hat and beta 2 hat for each of the sample that you got. Now, if I ask you how many samples would you get? Can anyone answer? All possible samples of size 10
100.
from population of 1000.
100, sir.
No, no. You can take all different combinations of 10 samples, all possible combinations of 10 samples. Okay, let me give you a simple example, not 1010.
The
These
questions
are
are
big
for
numbers. If I say uh, there is a population of 6, right? Or let us say there is a population of 4, and you have to collect all possible samples of size 2. Then how many samples would you collect?
for all the six.
6. So you will have a sample A, B. Suppose there are 4 elements A, B, C, D. You'll have a sample A, B, a sample that contains AC, another sample AD, another sample BC, another BD, another CD. These are all possible samples of 2, of size 2, right?
Yes, sir.
In that sense, I'm saying that there will be lots and lots of samples that are possible. If you do that, so you collect all possible samples of size 10 from the same population of 1000, of size 1000, and then you calculate beta 1 hat and beta 2 hat for each of the samples. And then if you plot that beta 2 hat, suppose, take one of them, let's take beta 2 hat, and plot all the beta 2 hats on an x-axis only, then and get a density function for that, or distribution, probability distribution of that, uh, you will have something like this. So you'll have lot of betas here, and suppose this is my x-axis and this is beta 2 hat axis, and I'm having my betas here. There are many betas taking this value, and you'll have a distribution like this, and there will be one value that would be occurring. Some values of beta 2 would be close to the mean. It will be some sort of normal distribution, and you'll get something like this. So these are all possible values of beta 2 hat that you can get, right? All the values have been plotted here. The height is nothing. There is nothing on the y-axis. This is on the y-axis. We have density basically, right? Density means that if beta 2 takes a value of 2, then all those beta 2s which are around 2 would be populated here, so that the height of the curve would tell you about the density, how many beta 2 hat values are at 2 and around 2. So there will be very few values having a beta 2 hat value of say 0, or let us say 1, and very few values after 3. All the beta 2 hat values are concentrated between 1 and 3, and most of the values are around 2, right? Something like this would happen, right? So anyways, this is the probability distribution. We call it sampling distribution. We call it sampling distribution. Why we call it sampling distribution? Because we are drawing this on the assumption that if we collect all possible samples of size 10 from a population of size 1000, then we would get these beta 2 hats, right? So this is based on the sampling. So it's called a sampling distribution. It is a probability distribution, and it shows some density function on the y-axis. Now, what is standard error? Standard error is the standard deviation of the sampling distribution of the estimator. Simple, that's the definition. So standard error is nothing but standard deviation. So you know what is standard deviation, right? Of what? Of the sampling distribution of the estimator. The estimator is beta 2 hat in this case, right? Sampling distribution, I just explained what is sampling distribution. So this is the definition of standard error, right? So I'll talk more about standard error next time. I would want you to have a good reading of this explanation of standard error from the book. This and more explanation is there. Just read about it before coming to class tomorrow, so that it becomes easy for me to make you understand the concept and calculation of standard error of beta 2 hat and beta 1 hat. Any question?
No, so
So standard error here means that the standard deviation of the sample.
Yeah, standard deviation of the sampling distribution of the estimator.
And
Not
so what
sample.
is sampling distribution then?
That's what I was explaining for the last 10 minutes, that if you collect all possible samples of size 10 from a population of size 1000,
Yes,
and
sir.
you calculate beta 2 hat for all the possible samples, and then you plot it like this, what you get is the sampling distribution of beta 2 hat. And if you calculate the standard deviation of all the beta 2 hats that you got,
Yes,
that
sir.
would be
That would be
the standard error.
the standard. So basically, so some if we can simplify a sampling distribution in some words, what it is the distribution of the uh, beta 2 beta 2
Yeah,
height
that
beta 2 height
that yes, that's the sampling distribution of beta 2 hat. You
through
can
which we
have
can find a
you can have
standard error.
You can have a sampling distribution of anything.
Okay, sir.
All what you have to do is to sample again and again and get all possible samples of a given size from the population of a given size, and then calculate its standard deviation to get the standard error of that thing, not only beta 2 hat, but anything,
Okay, sir.
right? So it's a general concept.
Okay. Thank you, sir.
All right.
So actually we have our next class, so can we switch to that link if it is okay?
Yeah, you can, but please let me know the list of absentees on the WhatsApp, Priyank.
So I believe everyone is present because there are 30 attendees.
Okay, then if that is the case, just put it there that no one was absent on the WhatsApp.
I'll
So that
do that.
mark, I'll.
And, yes, sir. And another thing, sir, could you please share the recordings with us?
Sure, sure.
All right, sir. Thank you so much.
Okay. Okay. All right, then you can leave now. Thank you. Have a nice day.